Welcome to Iron Process, where transformation doesn't announce itself loudly, but unfolds through systems you rarely notice at first glance. At a construction site, what you see is familiar: concrete, steel, heavy machinery operating in plain view. But what truly matters is not the material. The real evolution lies in how the entire process is structured, executed, and controlled behind the scenes. And it is this silent shift that is redefining how modern infrastructure is built. Following the Oroville Dam spillway incident, Phase 2 of the reconstruction marked a critical milestone in restoring and upgrading one of the largest flood control structures in the United States. The objective was clear: completely rebuild the main spillway while reinforcing the emergency spillway system to ensure safe performance under extreme hydrological conditions. The process began with the demolition of damaged chute sections, preparing the foundation for a new structural system designed for higher durability. The rebuilt spillway utilizes reinforced concrete slabs with an average thickness of approximately 2.3 meters. This is combined with rock anchors drilled up to 7.6 meters deep into the bedrock, significantly increasing resistance against high-energy water flow. The chute itself extends over 900 meters along a steep hillside, with a width approaching 55 meters. Reinforced concrete training walls are constructed along both sides, guiding high-velocity water flow downstream in a controlled and stable manner. Beneath these slabs, an advanced sub-drainage system is implemented to relieve internal water pressure. Reducing hydrostatic uplift and protecting the structure during flood discharge. Previously formed erosion pits were stabilized using roller compacted concrete, creating a solid base layer for the structural concrete above. The integration of RCC with cast-in-place reinforced concrete enhances overall durability across the entire system. At the base of the spillway, dentate energy dissipators are restored, engineered to break down flow velocity and disperse energy before water enters the river channel, minimizing downstream erosion. At the same time, the emergency spillway undergoes comprehensive reinforcement. A deep underground cutoff wall, formed by overlapping drilled concrete shafts, extends into the bedrock to prevent headward erosion. Additional RCC armoring and energy dissipation structures further stabilize the hillside under extreme conditions. Throughout the entire construction phase, thousands of engineers and workers operated continuously using heavy equipment to meet strict project deadlines. Upon completion, the system achieved a significantly higher level of safety and durability, capable of handling extreme flood events while protecting downstream communities. One of the most critical milestones was the final placement of concrete for the dentate dissipators at the spillway base. These structures are specifically designed to reduce flow velocity and dissipate energy efficiently before discharge. The operation was executed continuously over 5 days, with round-the-clock coordination between batching, transport, and placement teams. Concrete was poured into heavily reinforced formwork and mechanically vibrated to eliminate air voids, ensuring full bonding with reinforcement. Surface finishing was carefully textured to optimize hydraulic performance. Quality control engineers monitored every stage to maintain strict compliance with technical specifications. The result was a system with significantly improved energy dissipation efficiency and operational safety. At a broader level, methods such as box girder full-span casting represent more than construction techniques. They signal a transition toward industrialized construction processes. Instead of assembling piece by piece on site, structural components are fabricated in controlled environments and installed as complete systems. This approach minimizes tolerances and ensures repeatable quality. It is not just about speed, it is about precision at a scale traditional construction cannot match. Reducing on-site work also minimizes risks, improving safety and consistency. The entire workflow begins to function like a production line, where each stage is optimized and tightly integrated. This approach is not limited to large-scale projects. It establishes a foundation for modern infrastructure systems where precision and repeatability are no longer optional, but required. The launching gantry method used in girder erection is a clear example of this shift toward mechanization and precision in viaduct construction. Segments are lifted, transported, and installed at elevation using a main girder system and trolley mechanisms, completely independent of ground conditions. This allows uninterrupted operations below. The most critical stage lies in segment connection. Each segment must be aligned with high accuracy using surveying systems, combined with epoxy bonding and post-tensioning tendons to form a continuous structural system. Geometric tolerances and pre-stressing forces are tightly controlled, directly influencing load capacity and long-term durability. Operating in a repetitive closed cycle, the system ensures stable and predictable progress. This represents a fundamental shift in construction thinking, assembling structures with precision rather than building them piece by piece. The Doha Link project demonstrates this at a system level, where multiple construction components, casting yards, temporary trestles, pile foundations, and superstructure works are executed simultaneously in a tightly coordinated workflow. A centralized pre-casting yard enables strict quality control and ensures a consistent supply of girders. Meanwhile, the temporary trestle system acts as an offshore platform, maintaining continuous access and transport operations. At the technical level, offshore piling, pier construction, and pre-stressed girder casting require high precision and close coordination with heavy lifting systems to maintain construction momentum. Ultimately, project efficiency is not determined by individual operations, but by how effectively the entire construction chain is synchronized, where progress, quality, and safety are managed as a unified system. The Luma Arles Tower stands as a precise example of how complex architectural geometry can be translated into a fully buildable structural system. At its core, a rigid reinforced concrete structure provides global stability, acting as the primary load-bearing spine. Surrounding this core, an external steel framework functions as a flexible system, enabling the realization of non-linear forms characteristic of Frank Gehry's architectural approach. Each steel element and cladding panel is uniquely fabricated, requiring extremely tight tolerances during manufacturing, positioning, and installation. There is no repetition. Every component is a controlled variation within a larger geometric system. The stainless steel facade goes beyond enclosure. It operates as a dynamic, reflective surface, continuously interacting with light and viewing angles, redefining the building's appearance over time. From an engineering perspective, the challenge is not height or scale. It lies in maintaining control over complex geometry throughout every stage of construction, where the boundary between design and execution becomes nearly indistinguishable. Row Tower 2 presents a different type of challenge. High-rise construction within extremely constrained urban conditions, where efficiency and precision must coexist under constant limitation. The foundation stage begins with excavation exceeding 20 meters in depth, supported by board piles and a massive raft foundation. This establishes a highly stable base for a structure exceeding 200 meters in height, where even minor deviations at lower levels can amplify significantly as the structure rises. As construction progresses upward, the strategy follows a core-first, shell-later approach. The reinforced concrete core advances using a self-climbing formwork system, functioning as the central structural spine while enabling steady vertical progression. This system integrates working platforms, climbing mechanisms, and protective enclosures into a single self-contained construction environment at height. It reduces dependency on external scaffolding and improves operational control. One of the most critical performance indicators is the construction cycle. Initially requiring approximately 14 days per floor, the cycle is progressively reduced to around 6 days as processes become standardized and synchronized. This acceleration is not driven by technology alone, but by the optimization of workflow, where rebar installation, concrete casting, formwork stripping, and system climbing are executed in a tightly coordinated sequence with minimal delay. Logistics are handled through a strict, just-in-time delivery model. Materials arrive exactly when needed and are installed immediately, eliminating the need for on-site storage and reducing congestion within limited space. The integration of BIM from early stages allows the entire construction process to be simulated and coordinated in advance. Potential clashes are identified before execution, ensuring continuity across all stages. At higher elevations, environmental and technical constraints become increasingly critical. Wind loads, geometric tolerances, and equipment performance directly impact execution quality. To address this, systems such as wind shielding, digital surveying for vertical alignment, and high-precision concrete pumping are implemented. Every operation is controlled within tight tolerances, often at the millimeter level. From thick core walls to large-span floor slabs, each structural component is executed with high accuracy. This reflects a construction system where precision is not an outcome, but a requirement embedded within the process. These capabilities demonstrate not only the ability to handle complex technical challenges, but also the ability to organize construction as a synchronized and stable system across the entire project lifecycle. The early completion of structural works is not accidental. It is the direct result of comprehensive control, where planning, execution, and coordination operate as a single integrated system. From both technical and organizational perspectives, RoTower 2 is not simply a high-rise structure. It is a demonstration of how modern construction can achieve industrial-level precision even under the most constrained conditions. At Hoshima Port, the production of large-scale concrete units represents a different dimension of industrialized construction, shifting quality control from the installation phase to the fabrication stage. Instead of relying on unpredictable offshore conditions, the entire process is managed within a controlled production environment. One of the key aspects is the integration of advanced technology into operations. Load rotation control systems stabilize heavy components under wind influence, while AI-based camera systems provide real-time safety monitoring. These technologies do more than reduce risk. They improve precision when handling large structural elements in dynamic conditions. At the material level, the use of penetrating curing compounds replaces conventional curing methods. This shift enhances long-term durability, particularly in corrosive marine environments where material degradation is a critical concern. More importantly, the entire workflow is structured as a continuous production line. Each unit is manufactured to meet strict individual standards while maintaining consistency across the entire system. This ensures that when assembled, all components function together as an integrated energy dissipation structure. From a construction standpoint, this is not simply the production of heavy elements. It is a coordinated system where safety, precision, and durability are controlled simultaneously under demanding environmental conditions. The Visoda 239 facility represents a fully optimized system for manufacturing large-diameter steel pipes, where geometry, stress distribution, and weld quality are tightly controlled. The process begins with plate preparation, a critical stage that defines the quality of the final product. Ultrasonic testing detects internal defects. Shot blasting cleans the surface. High-precision edge milling ensures proper parallelism and weld geometry. Edge bending is then performed using forces up to 2 times 40 meganewtons, pre-curving both sides of the plate to prepare for forming. During forming, JCO presses with forces ranging from 6,500 to 10,000 tons apply sequential deformation. This controlled process enables precise diameter formation ranging from 508 to 1,422 millimeters, with wall thicknesses up to 45 millimeters. This stage establishes the initial geometric accuracy, which directly impacts weld quality and pressure resistance. The welding system is designed for both depth and efficiency. MAG tack welding stabilizes the structure, followed by submerged arc welding using multi-wire configurations, up to 4 wires internally and 5 externally. This configuration optimizes welding speed without compromising structural integrity, ensuring compliance with API and DNV standards. Non-destructive testing, including ultrasonic and X-ray inspection, is integrated throughout the process. Quality control is continuous, rather than performed only at the final stage. After welding, mechanical expansion using forces up to 1,500 tons restores precise geometry and relieves residual stresses introduced during forming and welding. End finishing and hydrostatic testing at pressures up to 600 bar verify structural integrity under near operational conditions. At the system level, a Level 3 MES enables full traceability. Each pipe is tracked through a unique identification system, integrating data from raw materials, processing parameters, and inspection results. This transforms every product into a complete digital record, enabling real-time quality control and long-term traceability. Chelpipe's implementation demonstrates not only advanced manufacturing capability, but also deep customization, with approximately 60% of equipment adapted to meet specific market requirements. From an industrial perspective, Visota 239 is not just a production facility, it is a fully integrated system where materials, geometry, and data are controlled as a single, unified process. erection of the MP3 tower block within the Kawasaki Port Coastal Line project demonstrates a highly advanced offshore heavy lifting operation executed under strict spatial constraints and rigorous safety requirements. With a structural weight of approximately 1,600 tons, the use of a 3,000-ton floating crane was not simply a lifting task. It required a coordinated system where equipment capability and dynamic load behavior had to be managed simultaneously within a marine environment. External factors such as wind, water currents, and barge motion directly influenced load stability. This demanded high safety margins in lifting systems and precise procedural execution at every stage. The most critical phase involved orientation and spatial positioning. The structure had to be rotated from a horizontal to a vertical position, then maneuvered into place between existing piers. This required simultaneous control across multiple degrees of freedom, including rotation, horizontal alignment, and vertical positioning. During lowering, oscillation control systems were applied to suppress movement, ensuring stable placement. Notably, erection tolerances were maintained within a range of plus or minus 3 millimeters, an extremely strict requirement given the scale and weight of the structure. This level of accuracy reflects not only advanced surveying and positioning capabilities, but also precise coordination between mechanical systems and human control. Final alignment adjustments were carried out using hydraulic jacks while the structure remained under load, further demonstrating the level of control required. Beyond technical execution, construction management played a decisive role. Coordinating floating cranes, transport barges, maritime traffic, and nearby airspace required a tightly synchronized operational plan. Every movement had to align with environmental conditions in real time. This was not simply an installation process. It was a controlled system, managing both load behavior and environmental interaction simultaneously. Light gauge steel construction using the FrameCAD system represents a different direction in construction, a fully digital, prefabricated building model. At its core is panelization. Instead of fabricating components on site, all elements are fully detailed in specialized software and directly transferred to roll-forming machines. This allows complete panels to be produced with tolerances of approximately 3 millimeters, including pre-integrated openings for mechanical, electrical, and plumbing systems. On-site modification is nearly eliminated. FrameCAD machines operate similarly to CNC systems for sheet steel, performing cutting, punching, and forming operations based entirely on digital input. The integration between design software and manufacturing equipment ensures that each component is produced exactly as modeled, removing dependency on manual workmanship. A major advantage lies in supply chain coordination. Panels can be manufactured in parallel with foundation work, allowing immediate assembly once the base structure is complete. This manufacturer-first approach significantly reduces overall construction time and minimizes idle periods between phases. Material performance is also improved. Light gauge steel maintains geometric stability, unaffected by moisture or deformation typically associated with timber, while reducing material waste through precise fabrication. This approach does not simply improve construction efficiency. It redefines construction as a production process where structures are manufactured with industrial precision and assembled at production line speed. Automation continues to expand into finishing works, as demonstrated by the YBUI Intelligent Wall Plastering Robot. This system integrates a pressurized mortar delivery mechanism with automated application control, ensuring uniform material distribution across surfaces. A laser positioning system continuously scans surfaces in real time, controlling flatness, vertical alignment, and plaster thickness within a range of 10 to 20 millimeters. The operation follows a continuous spray, compression, and leveling cycle, with controlled overlap to eliminate gaps and maintain surface consistency. A vertical lifting mechanism allows the system to operate up to ceiling height, ensuring uniform results across full wall dimensions. Despite automation, human involvement remains necessary in localized areas, such as edges and joints, where fine adjustments are still required. The significance of this system lies not only in productivity gains, but in transforming finishing work into a controlled and repeatable process rather than a skill-dependent task. Smart Timber construction technology introduces another prefabrication model, where structures are assembled using mechanical precision rather than wet construction methods. A screw pile foundation system combined with a metal beam frame creates a stable base without the need for excavation or concrete pouring. This significantly reduces construction time and site impact. A key feature is the threaded rod connection system, which compresses timber elements into a unified structural block. This minimizes shrinkage and ensures structural continuity. All components are prefabricated with high precision, allowing rapid assembly with minimal on-site error and virtually no material waste. This dry construction approach enables immediate execution and improves overall quality control. It represents a shift from traditional construction methods toward production-oriented systems where precision and repeatability align with industrial standards. Concrete demolition using MHB breakers demonstrates a controlled approach where surface layers are fractured through sequential impacts while preserving underlying structural integrity. The resulting fragments are efficiently handled using excavators and high-capacity dump trucks, forming a continuous material processing loop. By controlling fragment size at the demolition stage, loading and transport become faster and more consistent. This approach transforms demolition from a destructive process into a controlled recycling operation, where existing materials are treated as reusable resources. The Zitra system further optimizes material flow on site by transferring bricks directly from removal points to paving machines via conveyor systems. Combined with automated road printing systems, the process becomes a continuous construction line, reducing transportation requirements, minimizing environmental impact, and improving surface quality. Automation also extends to concrete floor finishing. The screeding robot ensures precise elevation and flatness control, using either automated positioning or remote operation modes. With a working width ranging from 1 to 1.5 meters, the system achieves productivity levels between 100 and 160 square meters per hour while maintaining required surface tolerances before concrete sets. Across all these applications, from dams and viaducts to high-rise buildings and industrial manufacturing, a consistent pattern emerges. The defining factor is not individual technology, but how the entire process is structured as a continuous, controlled system. Every stage, from design and fabrication to transport and installation, is standardized, synchronized, and optimized. Errors are minimized, quality is maintained, progress remains consistent. This is not simply technological advancement, it is a fundamental shift in construction thinking. As processes become digitized and managed like industrial production systems, structures are no longer built in isolated steps. They are produced as outcomes of pre-engineered systems, predictable, controllable, and repeatable with high reliability. In this context, construction capability is no longer defined by speed or scale alone. It is defined by the ability to organize and operate an entire value chain, where technology, workforce, and processes function as a unified system. This is how modern construction achieves industrial-level precision and efficiency. Thank you for watching until the end. If you found this valuable, make sure to like, share, and subscribe so you don't miss upcoming insights from Iron Process. See you in the next system.